A plane that needs no runway. An idea that has always been a fantasy of airplane designers. The Ryan X-13 Vertijet attempted to be runway-free, but proved impractical. It was the success of the Bell X-14 that paved the way for today's vertical takeoff designs. Lifting vertically off a ship's deck, the V-22 Osprey acts just like a helicopter. But by a marvel of engineering, it can do something a helicopter can't: transform into a high-speed, long-range aircraft. The Osprey tilt-rotor system is an answer to a problem that was a challenge to a whole family of X-planes. Not built for speed and altitude, but vertical flight. One of the first vertical takeoff and landing, or VTOL, X-planes was the Hiller X-18. Its whole wing could be tilted up. This thrust pipe aided control during a hover. First flown in November 1959, it was a short-lived program, but contributed to the development of yet another tilt wing. Built for use as a VTOL-capable transport, the Vought XC-142 was also a tilt wing, and in 1965 it successfully transitioned from a hover into level flight. It helped demonstrate the advantages of heavy-lift VTOL aircraft. Another concept was to tilt the propeller. The Curtiss-Wright X-19 was powered by two turboshaft engines driving four tiltable props through a complex gear system. First flown in 1963, the X-19 program was plagued with setbacks and ended in 1965 after an in-flight failure. Colonel Jesse Jacobs recounts the crash.
Gearbox failed, the propeller left the airplane started rolling and started down, and the guys punched out, inverted, rolling in excess of 200 degrees a second at 392 feet. It's amazing they made it.
In 1953, with a history of pioneer work in helicopter development, Bell Aircraft began exploration of the ducted fan. 14 years later, their VTOL ducted fan X-plane was flying. The X-22 was to have one of the longest test programs of the X-planes, with Bell building a totally new type of aircraft. Its four GE turbine engines drove the propellers via a system of 11 gearboxes. In some ways, a system similar to the one used in the ill-fated X-19. However, the X-22 would prove much more successful. Its four ducted fans were fully tiltable and could rotate from 0 to 95 degrees in under 20 seconds. The ducts acted like circular wings in forward level flight. There were large moving surfaces to the rear called elevons, which in concert with the variable pitch propellers created all the control the X-22 needed. The aircraft had no conventional flaps or ailerons, and had a vertical tail with no rudder. It was indeed a very different aircraft. Working around the X-22 was safe. With its propellers enclosed in ducts, the risk of propeller strike accidents was reduced. Pilot safety was also a consideration. Bell tested rocket-propelled ejection seats as an escape system in the X-22. After 6 months of static tests, the X-22 completed its first successful hover in March 1966. It could basically do anything a helicopter could, hovering and maneuvering in any direction. The question was, could it do what a helicopter couldn't? Transform itself into an efficient, fast, long-range aircraft. And unlike a helicopter, not have to rely on the brute force of its engine to keep it aloft? Simply put, could it cash in on aerodynamic lift to give it greater speed and range? By March 1967, the X-22A had transitioned from vertical takeoff to level flight, going to a maximum speed of 255 miles per hour with a 445-mile range. In July 1968, it completed a world record sustained hover at 8,000 feet. However, all these achievements belonged to the second of the two aircraft built. During a test flight in August 1966, the first X-22 had suffered a fatal blow when it mysteriously dropped into a field. The crew escaped uninjured, but the X-22 was beyond repair. But overall, the project proved a great success, and the remaining aircraft flew for many years. The X-22 proved the ducted fan a configuration for the future. In the 50s, pure jet vertical flight became a challenge worth pursuing. Jay Miller, aviation historian.
The big concern was the technology. In other words, could it be done? Yes, there had been some VTOL work done with propeller-driven aircraft. There was obviously a lot of VTOL research being conducted with helicopters, but pure jet VTOL was still an unknown entity.
In 1951, Ryan's unmanned test rig completed the first controlled jet hover. Wind tunnel tests were carried out on a delta wing VTOL jet. It was to sit on its tail for takeoff, then transition into level flight. The pilot's seat was set up like a Ferris wheel chair, rotating forward during vertical flight. As the concept was exhaustively tested, Ryan's first backer, the Navy, pulled out as a result of post-Korean War funding problems. Then the project was taken up by the Air Force, and the first X-13 Vertijet was completed by 1955. A Rolls-Royce Avon turbojet was chosen because it had the highest power-to-weight ratio of any available engine. In August 1955, the X-13 was hauled from San Diego to Edwards Air Force Base in the Mojave Desert to begin its test program. Its first flights began with conventional takeoff and landings to feel out the flight characteristics. These were completed with a temporary tricycle landing gear. In its final configuration, the X-13 would have no conventional landing gear at all. A special flatbed trailer was developed for the X-13 that could raise the aircraft to its vertical takeoff position. For early hovering tests, the X-13 was caged in a tubular steel rig called the Pogo. Control during vertical flight was provided by wingtip thrust nozzles, driven by the engine compressor. These thrusters worked along with another control system, truly unique to the Vertijet.
The exhaust nozzle was perhaps the major leap forward from a technology standpoint because it was an articulated exhaust nozzle. And with the pilot moving controls inside the cockpit, that exhaust nozzle moved in concert with that control movement, which also moved in concert with the control surfaces on these delta wings.
For its first transition flights, the X-13 was taken up to 6,000 feet. Here, the pilot was at a safe altitude if anything went wrong. As it hung in the air, the X-13 had become the first jet aircraft to transition to a hover from level flight. It seemed pure jet VTOL was possible after all. After high-altitude practice, the program turned to the problems of landing and takeoff from the trailer. Ryan test pilot Pete Gerard practiced over and over maneuvers close to the rig, and then the transition to level flight. It looked remarkably smooth and almost unreal. On April 11, 1957, after many months of careful preparation and practice, Pete Gerard and the X-13 were ready. The aircraft unhooked and steadily hovered away from the support trailer for the first time. The little jet had successfully taken off vertically, proving it was all possible. After transition to level flight and running through several conventional flight maneuvers above the base, Gerard descended back to Edwards. This was the hard part, to carefully position all 3.5 tons of X-13 supported only by a shaft of hot gas over a cable suspended in midair. Constant radio contact had to be kept with the pilot as he crept closer to the trailer. A retractable hook situated in the nose would make contact with a cable stretched between two articulated arms on the trailer. The X-13 was truly a bird on the wire. After the X-13's first true VTOL flight, it went on to perform many more, even putting on a show in front of the Pentagon, retracing a course flown by Orville Wright some 48 years before in the first military flyer. But the Vertijet would remain an experiment. By 1958, the project was over, having cost some $9.4 million. Funding problems, power limitations, and the conservative establishment of the time were to bury the program. Both X-13 survived their flight test program, and one is on display, hooked to its trailer at the San Diego Aerospace Museum in California, not far from where it was built. The X-13 was one of the earliest pioneers of jet VTOL, and lessons learned from it are still relevant today. Perhaps the X-13 was an aircraft a little too ahead of its time. The 1950s saw other jet VTOL concepts. Instead of turning the entire aircraft, why not just tilt the engine? This test model, built by Bell, was to be a tilt-jet VTOL fighter. The wingtip-mounted engine was able to thrust the aircraft up vertically, then tilt back for fast, level flight. The Bell Air Test Vehicle, or ATV, was built to test the theory of tiltable jet engines. In early trials, it was attached to a moving disc on the tarmac. This strange little aircraft was made up from scavenged parts: wings from a Cessna, fuselage from a glider, and two small jet engines built to rotate from vertical to horizontal flight. It also had a smaller turbine engine mounted above and behind the pilot. This supplied a system of reaction control thrusters on the tail and wingtips, designed to control and stabilize the aircraft during vertical flight. It first flew in 1954 after a carefully monitored ground test program. The ATV, although certainly an ugly duckling, holds an historic place in the jet VTOL story.
This kind of hybrid aircraft basically proved that a pure jet VTOL airplane could indeed be built. Now, the ATV never fully transitioned in flight, but it partially transitioned, and that's a very important issue. It's hard to understand that from our perspective today, where pure jet VTOL is not in the least bit uncommon with the Harrier and related aircraft. But in those days, that was still a major step forward.
The vast amount of data drawn from the ATV led Bell to take the idea a step further. Instead of tilting the whole engine, they would attempt to bend the jet thrust itself. The flight simulator for the Bell X-14 was very basic, but nevertheless essential in preparing pilots for a completely different way of flying. From these simple beginnings was born an aircraft that was to fly for over 24 years. Tethered tests began in 1956, and like the ATV, it was a hodgepodge of other aircraft. Controlling a hovering aircraft is complex. The X-14 used the same system of wingtip and tail-mounted thrust nozzles initially proven on the ATV. But instead of using a separate air compressor, the X-14 diverted exhaust gases from its jet engines. The wingtip nozzles controlling the roll motion of the X-14 were directed by the pilot. However, it was tested with an early computer system to help maintain stability. The tail-mounted nozzles worked in phase with the tail surfaces to control yaw and pitch motions. But the major leap forward was the X-14's ability to redirect or vector its jet thrust downwards. Rotating slotted vents or cascades diverted the thrust down for vertical flight. With a flick of a switch, the cascades could be returned to level flight position. This complex bit of engineering had never before been put to the test on any VTOL aircraft. However, a major problem arose. All systems were working fine, but the X-14 wouldn't or couldn't quite lift off.
It took them a little while to understand, but very basically, when the exhaust came out of the exhaust nozzles, these cascade nozzles, two things happened. Number one, a low pressure area was created underneath the wing of the airplane. And number two, the flow pattern was such that it wrapped around and came back on top of the wing. And the bottom line of these two things acting together was that the airplane could not really lift off the ground.
In the months to follow, many tests were completed to solve the riddle of the suck-down phenomena. With some subtle changes, the X-14 was soon making tentative hops into the air. The solution to its problem was strikingly simple.
There was an easy solution, and that was to just make the landing gear longer and thus get the airplane a little bit higher off the ground. And once that was done, sure enough, it proved to be the solution, and the airplane did fly successfully in VTOL mode, and it's one of the very first pure jet VTOL aircraft in the world.
On May 24, 1958, the X-14 completed its first full transition circuit, taking off vertically, entering level flight, and then transitioning back for hovering and landing. It could truly do what any helicopter could do, but with pure jet propulsion. The X-14 was to pursue many avenues of VTOL flight. For example, it was used to test VTOL landing surfaces. Dust and particles sucked into a jet engine could be very damaging. The idea of a portable landing pad that could withstand direct jet thrusts was explored. A ground crew would prepare a cleared area by spraying it with the heat-resistant material and allow it to dry. The easy handling and reliable X-14 was invaluable for studies like these. The Bell X-14 flew for over 24 years, the longest test program of all the X-planes, helping develop many VTOL systems. This strange-looking aircraft led the way for the world's most successful pure-jet VTOL fighter, the Harrier. Developed by the British firm Hawker, the Harrier uses a thrust vectoring system reminiscent of the X-14. Indeed, engineers drew from X-14 program experiences during the entire development phase, creating an aircraft that has flown for many years, proving itself again and again in combat. The Harrier's forerunner, the X-14, flew its final flight in 1981, the last X-plane to fly straight up. Out of the Cold War emerges the idea for a nuclear-powered bomber able to stay aloft for days and strike deep into the Soviet Union. With a working nuclear power plant on board and a lead-lined cockpit, the X-6 becomes the first truly atomic bomber. It's just one of many strange concepts in the X-planes program. The X-planes were all strange or peculiar in some way. Built as purely experimental aircraft, they dealt with phenomena never previously explored. Concepts involving aerodynamics, new materials, and human physiological effects were explored. But there were other, more eccentric X-planes that in some ways went beyond these extremes to explore even stranger avenues of flight. The X-6 project would explore the possibilities of unlimited range by using a nuclear power plant. The X-21A with its special wing would attempt to make transonic airflow play by its rules. The X-missiles laid much of the groundwork for modern missile technology and space systems. Such diverse projects were aberrations among even the strange X-plane family. The Bell X-9, or Shrike missile, was one of the first X-missiles to be air-launched. It was the testbed for the Rascal air-to-surface missile. From its first launch in May 1950, the X-9 would usher in many new ideas. Carried aloft by a Boeing B-50, the X-9 was swung down on a trapeze and launched in midair. X-9s were powered by two-chamber liquid-fuel rocket engines, pushing the missile to around Mach 2. It could range over 50 miles and then accurately hit its target, controlled by a radio technician in the B-50 mothership. The X-9 was perhaps the first weapon to marry the awesome power of a liquid-fuel rocket with the frightening, destructive possibilities of a nuclear warhead. Bell tried in vain to convince the Air Force to put the Shrike into production, but to no avail. Data provided by the X-9 program had proven the Rascal's basic aerodynamic configuration and the accuracy of the guidance system. The Rascal, although an early air-to-air missile of note, was only a stepping stone for later technology. The Bomark anti-aircraft missile was another with its roots in the X program. The Lockheed X-7 was used to test the Bomark's ramjet propulsion system. The large database generated by the X-7 project remains the foundation for much of our ramjet research today. The X-17 tested early space re-entry technology. During one flight, it reached a speed of over 9,500 miles an hour. Much of the data gathered by the 25 X-17 launches was invaluable in developing re-entry systems for ICBMs. The X-17 was also used during Project Argus, exploring the effects of nuclear explosions in space. One of the most curious X-missiles was the North American X-10. This remotely controlled missile on wheels flew by turbojet power beyond Mach 2. Built to test new aerodynamic and guidance systems, unlike other missiles, it could be landed safely after its mission.
It actually had some potential for becoming a manned vehicle. It was somewhat ahead of its time in being what today is referred to as a canard configuration, in which what we refer to as the tail surfaces were on the nose of the airplane instead of in the back end of the airplane.
The X-10 was the test bed for one of the milestones of space technology, the Navajo cruise missile. Going against the trend towards purely ballistic missiles, the Navajo project explored a very fast, flyable, aerodynamic missile configuration. The technology nurtured by this project was to have repercussions for many decades to come. New methods of building aircraft and space vehicles to withstand extremes of heat and cold. Also, uses of new construction materials like stainless steel and titanium were developed. New welding techniques, highly accurate chemical milling processes, the use of exotic alloys, along with a whole new era of electronics and precision component manufacture, grew out of North America's Navajo missile program. The Navajo would ride piggyback on a huge 90-foot-long rocket-powered booster that would be jettisoned after liftoff. For a ramjet to start operating, the oncoming air has to be traveling at high speeds as it enters the intakes. These engines would push the Navajo to Mach 3.25. By November 1956, the Navajo was ready. At Cape Canaveral, the missile and booster were lifted in place by a large pivoting gantry tower. First fired in 1955, the rocket booster produced 415,000 pounds of thrust. When the booster stage propels the missile fast enough, successful separation occurs. From here, the Navajo's huge ramjet takes over and pushes the missile to over Mach 3. Dealing with such extremes, the Navajo project was plagued by failures and was canceled in 1957. But the legacy of technology that sprung from the X-10 and Navajo was invaluable. Its rocket design philosophy would thrust the first U.S. astronauts into space. The guidance system helped navigate submarines under the North Pole, and its manufacturing techniques are still used today. The Navajo truly deserved its pet name, the Know-How Missile. This aircraft has very special wings. The turbulent layer of air that forms on the wing surface is inhaled through tiny slots. The X-21A's laminar flow control system was claimed to extend flying time to days instead of hours. Air resistance to the motion of the wing causes turbulence or friction grab. As the air passes over and under the wing and the cross-skin surfaces, laminar flow control reduces this drag by actually inhaling this turbulent air and disposing of it through specially designed slots. Many rows of tiny slots in the wing bring in the air. From there, it goes into the tributary ducts and then along through the main ducts. These ducts accept the boundary layer air drawn from the wing surfaces, then feed it through the modulating valve assembly into a low-pressure turbine-powered compressor, then on to the high-pressure compressor which expels it. In 1961, Northrop began conversion of two Douglas B-66s to the new X-21A configuration. The original engines were wing-mounted, but Northrop moved them back to the rear fuselage area to reduce noise and turbulence around the experimental wing. The compressors powered by bleed air from the aircraft's main engines were positioned under the wing. Laminar flow control's dividend was tantalizing. By reduction of drag, the engines would have a much easier time propelling the plane and need less fuel. Aircraft could stay aloft for days. Dreams of non-stop, unrefueled flights around the globe would be attainable. The razor-thin slots running wing root to tip were only about a 25,000th of an inch wide. Buried below them, 815,000 tiny holes drew air into the main wing ducts. The distinctive camel's hump wing section was an attempt to eliminate an airflow problem with high-wing aircraft. The surface of the wing was kept very smooth to further reduce friction. The aluminum skin was not riveted, but bonded by adhesives. During the early 60s, the X-21 consistently achieved clean laminar flow over 70% of its wing surface area. But in 1964, the project was canceled. Many flight tests exploring the impact of water, dust, and insects on the system proved the high maintenance needed to keep the slots free of debris couldn't be justified. Although a stunning success in theory and in the wind tunnel, laminar flow control could not work effectively in the real world. This concept of longer endurance aircraft would remain a dream. But around the same time, Convair was promising unlimited endurance. In Fort Worth, they began exploring the idea of a nuclear-powered aircraft.
On the one hand, nuclear weapons were these devices of extraordinary destructive power, and nuclear propulsion, on the other hand, was this clean, safe, unlimited, relatively cheap energy resource. And of course, as time has gone on and several decades have passed since then, we've all been rudely awakened to the fact that there are some very negative sides to nuclear energy as a power resource.
This General Electric built reactor was developed for the initial tests in the X-6 project. The NB-36H Crusader, a converted Convair bomber, would take the reactor aloft to explore safe methods of shielding from radioactivity. The reactor wasn't used to power the aircraft.
Well, that 1 megawatt reactor really did nothing. It just literally sat in the back of the airplane and reacted, and there was nothing that, to my knowledge, that was done with the power that was generated by that reactor. But on the other hand, it did develop or generate some radiation.
Great precautions were taken when the reactor was moved to the aircraft loading area. Many shielded support vehicles had to be developed. Even this huge crane was heavily shielded with lead, while carefully swinging the reactor over a specially built loading pit in the tarmac. The Crusader was chosen primarily because of its huge lifting capacity. The lead-shielded crew compartment weighed 12 tons on its own. Clearly, the road to a nuclear-powered aircraft would be one of extremes. During the Cold War paranoia of the 1950s, unsubstantiated stories of Soviet advances in nuclear-powered aircraft fueled support for the X-6 program. Convair was only one of many companies exploring the possibilities of an A-plane. The Crusader needed to be very precisely positioned over the loading pit. The pit was operated from a heavily shielded central control room nearby. Its doors were 7 inches thick and were mechanically opened for the loading only when the B-36 was in exactly the right position. The aircraft's bomb bay had been extensively modified with water-filled shielding tanks and an air cooling system for the reactor. The reactor was slowly winched up into the bomb bay. The process could take 20 minutes. After each test flight, it would be removed again for examination and as an obvious safety precaution. Mechanized probes on the motorized reactor platform were raised into the bomb bay to assure precise alignment of all connection points. A major part of these first test flights was to learn about safe ground handling procedures. The hazardous nature of just getting the reactor loaded safely required brand new technologies, foreign to conventional aviation.
Fortunately, most of the crew members, to the best of my knowledge, have survived, or if they have died, they've died of causes that had nothing to do with radiation.
Shielding of the crew had greatest priority. The 12-ton lead-lined capsule was well separated from the reactor located in the aft bomb bay.
The cockpit transparencies were pretty impressive. I think the forward transparencies were approximately 5 inches thick, and that was leaded glass. And then the side transparencies, which were particularly spectacular, they were over 11 inches thick. And again, that was all leaded glass. And there's always been the comment that, there was probably some distortion looking through that glass. And the answer, after discussing this with several of the crew members, yes, there was a lot of distortion looking out of that cockpit.
The Crusader made the first of its hot flights in September 1955. Loaded down with shielding and reactor, the takeoff weight was nearly 180 tons. It wasn't alone in the air. A C-119 flying boxcar followed the Crusader aloft, carrying a group of Marines with a special task.
If by some chance the NB-36H was to crash, those Marines would be effectively ejected out the back end of that C-119. They would parachute down to the crash site and surround the airplane to keep anyone from intruding into the wreckage site area.
Also keeping a close tail on the Crusader was a modified B-50, equipped to test for radiation emitted during the flight.
The whole thrust of the X-6 program was to develop an intercontinental bomber that basically had unlimited range. I mean, the whole philosophy was centered on that one very specific point. In other words, they could put an airplane in the air on alert, and it could stay in the air for an indefinite period of time. The only limitation really was your crew endurance.
During these initial tests, crew endurance and nuclear propulsion wasn't the question. Although the reactor was started by withdrawing the safety rods, at no time would it power the aircraft. It was simply there to test the shielding performance. The slow startup of a nuclear reactor would have made it necessary in a production aircraft to take off with normal fuels, then slowly transition to nuclear power. During reactor operations, data would be collected from instrumentation throughout the aircraft. The B-50 sensor aircraft following in the slipstream would check air patterns around the Crusader for any levels of radiation. After the test run, the reactor would be shut down in preparation for landing. Much was learned from the 47 Crusader flights, with Convair and many other companies building up an impressive technology base. But from the start, the X-6 project was always a hot potato. Support for the project was eroded by the massive costs and the obvious disastrous possibilities if an accident did occur. But for all its potential for disaster, very little did go wrong. One incident was an electrical fire in the bomb bay during a test flight.
It was a very minor fire, but at the time that it occurred and with a functioning nuclear reactor on board, it was a pretty exciting occurrence, according to the crew. And of course, the news media was never given any indication that that event had taken place until many years after the fact.
The Crusader's final flight took place in 1957. By the early 1960s, the U.S. nuclear-powered aircraft program had all but vanished. A suitable and safe power plant deemed beyond realization. The idea of a billion-dollar bomber that could stay airborne for months was no comfort for the Russians. But neither was the new crop of cheap and effective missiles. The X-6, perhaps the strangest technological misadventure of the X-plane series, was fortunately never to become a reality.
August 6, 1945. The day warfare changes irreversibly. It is not the result of a battleship or a fighter plane. Instead, it comes from a device less than 10 feet in length and 3 feet in width. Dropped from a B-29 Superfortress, the bomb known as Little Boy is the first atomic weapon to be used in history. Alongside its accomplice, Fat Man, these two weapons of mass destruction pulverized the Japanese, as two cities are obliterated. Now, the world led by the United States and the Soviet Union enter a new and frightening age where just one bomb can wipe out an entire population. With the Second World War ending and the Cold War beginning, America and the Communists start a massive buildup of this new technology. The race is on, where whoever possesses the most deadly arsenal of atomic force prevails. On both sides of the Iron Curtain, nuclear weapons become the ultimate symbol of strength and might. And during this period of intense Cold War anxiety, the idea of having aircraft fueled by this new source of energy is given the green light. If a nation can power homes and submarines with nuclear power, will planes be next? Having an atomic reactor on board has endless possibilities. Unlimited range, and the ability to be anywhere in the world in a matter of hours, ready to strike. Truly awesome aviation that will determine the #1 superpower. Unfortunately, this concept is easier said than done. Placing a nuclear device on an aircraft is both complicated and extremely dangerous. Can American scientists and aircraft designers overcome these obstacles? Can they prove the skeptics wrong? This is their story. The United States' decade-long saga to produce the first nuclear-powered aircraft. Prepare to experience the atomic-powered plane.
We are gathered here, representatives of the major warring powers, conclude a solemn agreement whereby peace may be restored.
With the Japanese surrender on the USS Missouri, Americans are both victorious and confident. The war they have been fighting for over 3 years has finally ended. They have emerged a superpower with what seems to be an unlimited industrial capacity. The nations of Europe are no longer the power brokers they once were, for it is the United States and its ally the Soviet Union that remain strong at the end of the Second World War. But just as this conflict ends, a new and more deadly struggle begins, as Nazism is replaced by communism as the greatest threat to Western democracies.
Nobody really knew a grand vision for Europe, even as Nazi Germany collapsed. There were still large questions as to territory, peoples, the movement of peoples, and exactly how this would all work out. The grand strategy with Franklin Roosevelt's the the famous spheres of influence, which means nothing, everything and nothing at exactly the same time. And that's where the roots of the Cold War come in big. There was a lot of tension and a lot of questions on both sides as to how it would all work out.
With this shift in the balance of power, the Soviets are no longer America's ally. They are now the enemy. And for the next 50 years, tensions between the two superpowers are felt beyond the capitals of Moscow and Washington, D.C., as the world is divided between capitalist and communist. Whoever can win the hearts and minds of those around the globe will emerge victorious. As this new Cold War takes shape, people begin to realize that America's victory over Japan has become a double-edged sword. The dropping of an atomic bomb, the nuclear genie has been let out of the bottle.
Well, world reaction was stunned. I mean, this is, I think, even at the time and place, a realization that it was a monumental event, even though nobody really understood what had taken place scientifically or even politically, even with respect to the war. It was unclear. But I think most people understood, and my read of the press in particular at the time was an acknowledgement that this was really big. This wasn't just any sort of military adventure whatsoever. But it's important to keep in mind that almost nobody, including the men who made the decision to drop it and the scientists who worked on the project, understood its ramifications in full. And I think it's useful to, remember Einstein, right, saying, I don't know how they're going to fight this war, but I guarantee you how they'll fight the next with sticks and stones.
Fearing the Soviets will be next, Russian scientists begin a mad rush to acquire this technology. What the United States possesses, they must equal and better it. It is unlike any other arms race in history. The end result could potentially wipe out 1/2 of the world's population, and even more. For this reason, it is vital that both nations attain as much nuclear technology as possible to deter the other from striking. As a result, rigorous testing is done on both the American mainland and on strategic outposts like Bikini Atoll.
The B-29 Dave's Dream takes off from Kwajalein to deliver the bomb, equal to 50,000 tons of TNT, while an electric metronome counts the final seconds. Cover your eyes. Now, on away!
To calm public fear of atomic power, every attempt is made by the United States government to emphasize the positive aspects of this new source of energy. Nuclear power plants are constructed across the country as a sign of progress and achievement. President Eisenhower goes to the United Nations with the idea of using atoms for peace.
The United States pledges before you, and therefore before the world, its determination to help solve the fearful atomic dilemma, to devote its entire heart and mind to find the way by which the miraculous inventiveness of man shall not be dedicated to his death, but consecrated to his life.
You have to understand the atomic aircraft project as part of the pentomic era. The 1950s, late 40s and early 50s, when everything that could be atomic was being turned into an atomic thing. There was atoms for peace. There was the idea that energy would be so cheap you couldn't meter it. You wouldn't have to meter it. Anything that could be powered by the atom was to be powered.
Despite these efforts, many are still skeptical about this source of power and its deadly ramifications. These fears are amplified with the development of Project Pluto, a nuclear-powered missile designed to unleash fission fragments all over the Soviet Union. Dubbed the Flying Crowbar, this weapon is considered too extreme even for the most hawkish Cold Warrior and is abruptly cancelled. Looking at the carnage of Hiroshima and Nagasaki, numerous Americans fear this technology throughout the 1950s.
What's it like, Chaplain? First of all, one sees a very, very bright light, followed by a shock wave, and then you hear the sound of the blast, and then it seems as though there's a minor earthquake. And then you look up and you see the fireball as it ascends up into the heavens. It contains all of the rich colors of the rainbow, and then as it rises up into the atmosphere, it turns a beautiful pale yellow, and then assembled into the mushroom. It's a wonderful sight to behold.
Hoping to end these concerns, in January of 1954, the USS Nautilus becomes the first naval vessel to safely enter the nuclear realm. With an atomic reactor powering the submarine, it can stay submerged for months if necessary, giving the United States a huge advantage over the Soviets in case trouble erupts. With this advancement, many are asking if it can work for an airplane as well.
And that's what somebody got the bright idea. Well, nuclear power, you can run a submarine, why can't you run an airplane?
Much will be learned here of the workings of atomic engines, not only for submarines, but for many peacetime uses as well. For passenger and merchant ships, for land transportation, for electric power plants, even perhaps for the huge airplanes of the future.
Submarines are not constrained by the same weight limitations as an airplane. So you could put a 10-ton reactor in with 100 tons of shielding, all wrapped around it in something that need only float. It's a completely different physics principle. And so therefore you have the space in the submarine for large reactors, large shielding, and large cooling systems.
It appears that what the Navy has been able to accomplish, the Air Force is going to have a harder time replicating. Despite all the doubts and skepticism, the decision to combine atomic energy with aviation is approved. Just like how the Liberators and flying fortresses that destroyed German cities mercilessly played an enormous part in winning the war in Europe, and how the constant bombardment of Japanese cities by B-29s was essential to American victory in the Pacific, perhaps a new bomber, powered by nuclear energy, will defeat the Soviets. For this reason, it comes as no surprise that many inside Air Force circles are eager to have a plane powered by the atom up in the skies as soon as possible. Across the Atlantic Ocean, the United States Navy hopes the same Anglo-American cooperation that produced the P-51 Mustang can result in their own version of a nuclear aircraft. Looking for the biggest plane Britannia can offer, both countries study the possibility of converting the gigantic Saunders-Roe Princess flying boat, a plane whose time has passed, into a device given its second wind by nuclear power. A key advantage of this concept is its range. Just 1 pound of uranium-235 is the equivalent of over 250,000 gallons of jet fuel.
With the end of World War II and the start of the Cold War, they now needed a bomber that could reach the Soviet Union from the United States. A nuclear-powered aircraft would not be limited by a fuel load, so it was desirable from that point of view.
With 30 million horsepower, theoretically, the aircraft could be up in the skies far longer than any conventional bomber in the US's arsenal.
Would sort of loiter over somewhere, US soil, presumably for days or weeks on end, possibly. Sort of simply be there as a warning.
So despite fears of nuclear annihilation, both the Air Force and the American government approved the project to develop this plane. In May of 1946, the Nuclear Energy for the Propulsion of Aircraft, or NEPA, is created. Where in the secret atomic city of Oak Ridge, Tennessee, the first stages of development begin. Looking for a company to start testing, Washington goes to one of its very best, Convair, makers of the massive B-36 Peacemaker. They are awarded the contract to begin designing their version of the atomic-powered plane, which after more than a decade of research and development, they dub the NX-2, an aircraft that looks eerily similar to North American Aviation's B-70 Valkyrie. The question is whether they'll use a B-36 or the new revolutionary jet-powered B-60 to begin their preliminary tests. An act of divine intervention makes this an easy decision for Convair when a tornado rips through Carswell Air Force Base, damaging a fleet of peacemakers. With little to lose, it is after this natural disaster when the choice is made to repair one of the B-36s, named the Crusader, and turn it into a nuclear-powered bomber under the Plan X6, with the General Electric Corporation chosen as the company to build its reactor,
the US Air Force had a nuclear reactor installed aboard a Convair NB-36 bomber. The nuclear reactor did not fly the aircraft. It had its own engine. It was simply there as an experiment to see, for example, the thickness of shielding required to protect the crew from long-term exposure to radiation.
A key roadblock in the plane's development comes from the radiation it will emit. Anyone standing within 100 feet of the core reactor unprotected is in store for a lethal dose of radioactivity. On land, nuclear power plants are shielded by more than 6 feet of concrete. In the skies, however, this shielding is too heavy for any aircraft, including the B-36, to sustain.
The single largest problem with an atomic-powered aircraft is that a reactor requires much shielding. Roughly for every ton of reactor, you require 10 tons of shielding. This was the case in the NB-36 program. A relatively small reactor required a cockpit shielded with 12 tons of lead and lead crystal glass just to protect the crew from the radiation emitted by the reactor.
And for it to be economically feasible, it must be able to carry a payload bigger than the B-52. For nuclear aviation to become reality, these barriers must be overcome by its designers. With this in mind, Convair's still unbuilt NX-2 places its pilots and crew far away from the reactor, hopes that less shielding will be required. But even if this is accomplished, there are still questions surrounding the heat generated on board the plane. Producing more radiation than a nuclear power plant into such a contained space has scientists worried that the intense temperatures are going to melt away the aircraft's interior.
There was no real way at the time to fix these problems, much as there isn't now. The shielding still grossly outweighs the reactor, and it turns out there's really no need for it.
Just like the Navy and its Princess flying boat, the Air Force is slowly realizing that the plane and the atom don't mix. Adding to these problems is many people's fear with all things nuclear. With the possibility of an entire city being wiped out with the flip of a switch, there are grave concerns over what happens if the plane crashes. If a hot reactor falls on a heavily populated area, the civilian casualties could be enormous. With this in mind, every precaution is taken when the NB-36 is sent out on a test flight.
We had a B-50 as a chase airplane to follow us in flight. Then they decided if we had to, for instance, an accident, what were we going to do? Well, they decided we've got to have some paratroopers to follow us down. We had C-19 to carry paratroopers. And we landed. All of this was secret.
Eventually, for a number of reasons, safety, cost, practicality, the nuclear-powered aircraft never got off the ground.
With this concept all but dead, it is miraculously brought back to life when a report surfaces that the Soviets are building their own version of an atomic-powered plane, in the form of a modified Tupolev 95.
One of the big pushes for this project happened after the NB-36 had stopped flying. In December 1958, the very important magazine Aviation Week, now called Aviation Week in Space Technology, published an editorial with photographs that they said were of an atomic-powered aircraft being flown in the Soviet Union. They had these drawings that even showed the big red stars on the side of the aircraft. Turned out to be a complete falsehood, a complete lie, and it's now thought that it was put out by the contractors and the Joint Committee on Atomic Energy, who were trying to push the atomic aircraft program through Congress and to force the U.S. Air Force to accept it.
Many of the cutbacks have not been justified. I would not want to condemn all. I know one which I regard as very damaging indeed, the cutback and the stretch out of the atomic airplane program. If our technicians were permitted the money and the authority to go ahead, they could fly an atom plane next year. Under the Take It Easy program of the administration, however, we are not scheduled to fly an atomic plane before 1964, if then. I doubt if the Russians will wait that long.
Afraid of another Sputnik, the American government assures its people that with each passing year, a nuclear-powered aircraft becomes more of a reality. while behind the scenes, its designers know the project is impossible to achieve. One major blow comes from President Eisenhower, who fights to end this plane before it consumes hundreds of millions of dollars more in appropriations. But perhaps the biggest nail in the NX-2's coffin comes from a Boeing -80 prototype.
In 1957, the last year that the NB-36 was flown, the U.S. Air Force introduced its first KC-135 tankers. 3 years later, they had 400 of these aircraft, servicing as airborne refueling stations for B-52s. They could now reach any part of the Soviet Union from the United States without landing. The idea that you now needed a reactor to do this was over, and the U.S. government realized the project was essentially dead because they already had the bomber force that they wanted.
With KC-135s and B-52 Stratofortresses, by the end of the 1950s, patience is wearing thin for a nuclear-powered bomber. After spending more than $500 million, and with no end in sight, the project is now on the chopping block. As one politician is overheard saying, it has been marked by a lack of well-defined objectives and by administration indecision. The optimism of the late 1940s and early 1950s has vanished. And when a Defense Department official tells the media that the plane's price tag will be over $10 billion when finally completed, the NX-2's days are numbered.
The world is very different now.
In 1961, as the Eisenhower era ends and John F. Kennedy is sworn into office, the project receives its final nail in the coffin when the aircraft, like many other Cold War creations, is terminated.
At the end of the day, heavy atomic reactors don't really belong on aircraft, and aircraft with refueling can reach their targets anywhere in the world. A reactor was simply found unnecessary to do the job the U.S. Air Force wanted to do.
Like many other Cold War concoctions, the atomic-powered plane represented thinking big. During a time when many thought that nuclear energy was the future for transportation, it was almost inevitable that an endeavor of this magnitude would be undertaken. With America and the Soviets on the brink of complete annihilation, aircraft like these were given the go-ahead, despite its impossibilities. In the end, the atomic-powered aircraft became the quintessential example of a military-industrial complex run amok, where profits were placed above people, and where Convair was placed above common sense.
The origin of the Vigilante program can be loosely traced to an event that would become America's answer to Pearl Harbor. On the afternoon of April 18, 1942, Jimmy Doolittle and his crack volunteer group prepared to embark on a surprise attack on Tokyo. This was no ordinary air raid. The attack was to be carried out by 16 Army Air Corps bombers.
As the carrier plows through heavy seas, one bomber after another soars from the flight deck, pointed for Japan. The sea grows rougher, the weather worse, but not one plane fails to get into the air. Taking the gale in its teeth, each bomber sets its course for carefully prearranged military objectives in Japan.
Deployed from an unlikely airstrip, the USS Hornet, the events of that rainy afternoon were unprecedented, not only because of the unique inter-service cooperation, but it proved that a Navy carrier was an effective platform for long-range bombing. The American strategy was effective. Doolittle's raiders had dealt an important psychological blow to a seemingly invulnerable adversary. The role of the aircraft carrier in this attack would not be forgotten. Just 3 years later, American planes again dropped bombs on Japan. Only this time, the symbolism of the attack was overshadowed by the destructive power of the weapon used. The onset of a nuclear age brought with it a change in military thinking. Having delivered the final blow to Japan, the U.S. Air Force assumed the mantle as the sole possessor of the nuclear endgame. As a post-war euphoria gave way to a Cold War reality, the Boeing B-47 and later Boeing B-52 Stratofortress were fit with the role of nuclear delivery. long-range strategic bombing became a defensive priority. Now equipped with an aircraft that could reach the Soviet heartland from American bases, the aircraft carrier was deemed redundant. Struggling to find a role in the era of the strategic bomber, the Navy put forth a nuclear-capable aircraft of its own. The North American A.J. Savage was clearly the result of the desire for a nuclear bomber combined with an inherent distrust of pure jet aircraft. The two propulsion engines provided the security of low-speed carrier operations, while a single jet engine mounted in the center of the fuselage provided the speed, with two turning and one burning. The Savage was a clever hybrid. However, by the time it reached the carrier decks, it was already becoming obsolete. By 1949, the Douglas Company had begun developing its jet-powered follow-on, the A-3D Sky Warrior. When the Navy ordered the Douglas Sky Warrior in 1949, it was clear that pure jet propulsion was gaining thrust aboard carrier decks. Like most early nuclear bombers, the Sky Warrior was a massive plane. 76 feet in length and 72-foot wingspan made it the largest plane ever to be deployed from the deck of a carrier. However, like most early large jets, the Sky Warrior was relatively slow. Unable to reach supersonic speeds, it was deemed vulnerable to rapidly improving Soviet air defense. Because of its sheer size, the Sky Warrior was disliked by deck handlers. The absence of an ejection system was unsettling to its 3 crew members. In fact, many pilots joked that the 3D stood for all 3 dead. While the mammoth Sky Warrior assumed the more passive roles of electronic warfare and tanking, the Navy set out to find a nuclear bomber that would go faster than ever before. At the North American Aviation Plant in Columbus, Ohio, the challenge of creating a new nuclear bomber was given full priority. Headed by Frank Compton, the Columbus designers took the initiative in preempting the Navy's request for a new bomber. Beginning with sketches and slide rules, the small group delved enthusiastically into the uncharted waters of the aerodynamic unknown. By 1954, the implications of technological growth had a profound effect on the American bomber tactics. Advancements in radar-guided surface-to-air missiles had all but nullified the safety of high altitudes. With this in mind, the Navy conducted a secretive mission to explore the alternative to a high-altitude nuclear attack. On this mission, an A.J. Savage would take off from Spain, fly all the way to Paris, and back. Under the French radar, the plane was never detected. The implications of a low-altitude penetration for nuclear delivery were noticed by the engineers of Columbus. This low-altitude requirement was not incorporated into their initial design, which was dubbed the North American General Purpose Attack Weapon, or NAGPA.
We initially designed a low-altitude version with all of the systems in it, the inertial navigation, the automatic systems, we had the rocket engine in it, and all of those things. And we called that the NAGPA, and that was presented to the Navy in 1953. So the Navy studied it. It was our own unsolicited proposal, and they thought, well, that's a good idea to do all of those things, which we ended up doing in the Vigilante, but they said, how about making it supersonic? So we packed our bags and went home for about a year, and then came back with a supersonic version, which is the present-day Vigilante.
The North American design was dubbed the A3J. The intended role of the A3J was simple. It would penetrate the Soviet heartland, bringing with it a nuclear bomb. Its blazing speed would be the key to its survival. The quest for higher speeds resulted in an airframe like no other at the time. North American test pilot Ed Gillespie remembers his first impressions of the Vigilante.
In those days, we always felt if an airplane looked good, it was going to fly good. Well, the Vigilante certainly looked good. It looked like it was going Mach 2 and it was sitting on the deck. I couldn't believe that our engineering staff could stuff all the goodies in it that they finally did and still make the airplane carrier suitable or have the range or the legs that we finally ended up with. But it was such a good-looking airplane, and it still is to this day, that you just wanted it. It was a Cadillac of the fleet.
The Navy's requirements were stringent, to say the least. The Vigilante needed to be launched from a carrier with 0 headwind, yet it also needed to cruise beyond Mach 2. Aerodynamically, this was a contradiction. The lift required for the carrier takeoff suggests the need for larger wings. However, larger wing areas prevent the plane from reaching high speeds. Engineers cope with this dilemma by making the wing much thinner than was generally accepted. It was argued by some that the aerodynamic compromises put forth in the Vigilante were drawbacks created by an overly stringent Navy. After all, since the aircraft carriers are generally moving, it would be extremely rare for a plane to be catapulted with 0 headwind. This requirement was later relaxed, but not until after the engineering staff had taken extraordinary steps in making a flexible airframe that would revolutionize the way military aircraft are designed. While the Vigilante was taking shape, the Air Force was making progress on their own supersonic bomber programs. Aircraft evolution during the Cold War was rapid. The mighty B-52 was soon to be outperformed by the B-58 Hustler. The Hustler was not only supersonic, it could fly at Mach 2. However, just as the Hustler was entering service, the Air Force began the quest for even higher speeds. Here, at the North American Aviation Plant in Palmdale, California, a new airplane was taking shape. The B-70 Valkyrie promised to be the fastest bomber in the world. The Strategic Air Command was enamored by its potential. By 1964, they would have a bomber that would be impossible to catch. "9,000 miles away, the American bomber programs were already making an impression. The American pursuit of supersonic bombers posed a great challenge to the Soviet military. Soviet airspace was immense, and an unwelcome bomber could penetrate the vast areas between air bases guarding the border. If a Mach 2 bomber were to penetrate, it would be nearly impossible for even the fastest Soviet fighter of the time to catch it. Soviet aircraft design bureaus revolted into the task of creating the ultimate fighter, a plane that could catch and destroy America's fastest bomber. Back at the Columbus plant, the Vigilante was beginning to take shape. By 1958, it was clear that this plane was revolutionary. It was the first plane to fly by wire controls, the first to have a heads-up display, terrain avoidance, and a fully integrated inertial navigation, bombing, and electric warfare system. Advanced aluminum alloys were also introduced. However, of all the Vigilante's firsts, there is one that few people know about.
One of the things that we did in 1955 was look at the so-called stealth characteristics of the airplane, which now are high tech. And we checked the airplane. We built a range out here on the airfield where we could put a model and we could rotate the model. It was a copper screen model, and impinge radar signals onto it and measure the feedback. So we would rotate the model, and we actually designed the airplane so that its radar reflectivity was concentrated at 2 points off of each side of the wingtips. And of course, when you're flying by something, why, you get a flash, but you don't get a large response. So we actually designed stealth into the Vigilante.
Back in Moscow, the design bureaus of MiG and Sukhoi were commissioned to develop an interceptor that could deal with the American threat. Despite differences in both culture and language between the United States and the Soviet Union, aerodynamics are universal. When different engineers independently strive for a similar requirement, their conclusions will also be similar. Therefore, it should come as no surprise that as early as 1958, the same year that the Vigilante first took to the air, Soviet engineers were filmed studying a model similar in design to that of the Vigilante. Despite the work done by Soviet designers on their own, it is likely that Columbus, Ohio frequently became the unofficial host of the KGB agents. It would be hard for them to miss the sleek American bomber sitting out on the tarmac.
They could have stood out here on the airport and taken pictures of it in 1958 when we made our first flight. There's really nothing covert about the Vigilante as far as its being there, and certainly the characteristics of it were secret. But the shape of it, looking at it, so I'm sure they had plenty of people, which they had all over the world, standing out here at Columbus, taking pictures of every airplane.
Nikolai Matchuk and Lev Shalengaya of the MiG Design Bureau were put in charge of the Soviet answer to the American bombers. An interceptor needs to be faster than the plane it chases. Therefore, MiG designers began the ambitious construction of a fighter that could push beyond Mach 3. This daunting task faced by the Soviets was aggravated by the progress being made back at the States. On the last day of August 1958, North American test pilot Dick Wenzel took to the air over Columbus. After the maiden flight, the Vigilante's prowess as a speedster began to truly shine. In June of 1960, famed aviatrix Jackie Cochran climbed into the back seat of the Vigilante, becoming the first woman to fly beyond Mach 2. Later that year, the Vigilante set yet another record when Commander Leroy Heath climbed to over 91,000 feet while carrying a 2,200-pound payload. Although the Navy was enamored by the Vigilante's performance, certain residents of the southeastern Ohio were less impressed.
We broke a lot of windows in the early days. One lady sued us because of the loss of her parrot, had a heart attack, I recall that. We also had a very definite problem with a gentleman down in southeastern Ohio who owned a dynamite factory, and it was right under our supersonic corridor. And he finally realized who was causing he was losing so many man hours to people bailing out the windows and so on when we would shock his employees that he finally got in touch with us and said, please, I think it's you guys, don't do it anymore. And indeed, we did move our corridor away from him, and he thanked us. He wasn't losing the time anymore.
To a pilot flying a new plane, the ejection seat is the most important piece of equipment on board. Bucking the trend toward the British Martin Baker variety, North American designed its own. And in fact, came up with the first seat to safety eject the pilot both above and below the speed of sound. A Navy pilot is not necessarily in the air when he needs to get out of the plane. In the dangerous world of carrier operations, escaping from a submerged plane can be the key to survival. Dramatic footage shows both crew members successfully ejecting at zero altitude, however the system was not error-free.
One time, I was flying at 42,000 feet on a first production flight, and a misrigged canopy, and this is the only time it ever happened, I might add, suddenly blew off. I lost my canopy at 42,000 feet at 1.42 Mach. And of course, it was stunned me. It just explosive decompression. I was alone. Explosive decompression. And when I realized, I thought I had ejected. But seconds later, I realized I hadn't. I throttled back, speed brakes out. My visor was down fully. My mask was on very tight. Of course, explosive decompression kicked it out. But when I finally got out of control, I realized it was still in the airplane, and the airplane was unhurt, except that I was open cockpit. So therefore, I claim, and nobody's ever I don't believe that anybody's ever come close, but we have the fastest open cockpit flying record.
At the beginning of 1961, 2 Vigilantes were moved from Columbus, Ohio to Kirtland Air Force Base to begin the program's most difficult and complex series of tests, on delivery. The method employed to release a bomb remains perhaps the most bizarre chapter in the Vigilante story. Instead of dropping bombs like a conventional bomber, the bomb was ejected straight out through an opening in the tail of the plane. In the early 50s, high and fast were the most important elements in a bombing attack. However, with improvements in air defense systems, it became apparent that sneaking under the radar was the safer bet. For pilots carrying a nuclear bomb, this meant learning some extraordinary tactics.
Our initial method was to fly the airplane straight and level at Mach 2 at 70,000 feet and drop the bomb out of the back of the airplane. As it would come out, the tail cone would come off the airplane, the bomb would come out like this and then go. And of course, the airplane was at 70,000 feet, so there wasn't an escape problem up there. Later on, of course, then we also decided that we could come in low, right on the deck, and pitch and automatically or manually program the airplane up and to about a 40-degree attitude where the bomb would then come out, and as the airplane continued, the bomb would come off and go towards the target. The airplane would then continue around and do an Immelman turn and then go the other way and escape. The other way was an over-the-shoulder where you hit the target, you were right over the target. This was your IP, or your initial point. You pull up right there and right over the target, you released the bomb, you continued around like this. The bomb would go straight up and come straight down, and luckily by the time it hit you, you were off and away.
For pilots, these hair-raising maneuvers were taxing enough without having to worry about finding and hitting the target. This was a job for the Radar Attack Navigator, or RAN, who sat in the back seat. Responsible for target and checkpoint acquisition, terrain avoidance, and a host of other duties, the RAN is crucial to the mission.
The fact that the RAN, or the Radar Attack Navigator, was in a compartment completely isolated behind the pilot with no front view meant that you had to work very hard at coordinating the mission, getting your cockpit-to-cockpit chatter down to where it was both brief but informative. And as the navigator in the back would run sensors, navigate the airplane, the pilot in front is looking for visual cues and maneuvering the target in the end game. It was a wonderful experience to form the teaming that you saw between pilots and navigators.
Before each mission, the RAN sets the course the pilot will follow en route to the target. Flying below radar means that mountains are as dangerous as the enemy defenses. This is especially true at night or in poor weather. Former Vigilante pilot Captain Joe Dyer is well aware of the importance of the man who sat behind him.
Well, I think the RAN that is responsible for me being here today was made up for one of those lapses in attention. I was a young aviator. We were flying low altitude and high speed, and after a few hundred hours, you got too comfortable at doing that. And I was looking down at a chart or my kneeboard card. The nose of the airplane dipped a little bit. The guy in the back seat says, "Hey, Joe, watch your attitude." I looked down 50 feet. Recovered. Nighttime, by the way. I gently recovered. Didn't say anything about it, but my knees were knocking in the front, and I remember thinking as we turned to the next target and the navigator was talking to me, "Gosh, you ought to be quiet. You know, you're almost dead back there."
During an attack, checkpoints such as islands or mountains were displayed on a television system. Such checkpoints were used to ensure the pilot was keeping true to course. Because onboard radar defeats the purpose of trying to remain invisible, the navigator was given a state-of-the-art interior navigation system that provided him an accurate reading of his location, without betraying his position. To ensure that the plane was keeping true to its course, the navigator would occasionally flash his radar to verify checkpoints and correct any navigational error. Should enemy interceptors pick up the radar flashes, an electronic countermeasure indicator will warn the pilot of incoming fighters. It will then confuse enemy radar by emitting false information concerning the whereabouts of the Vigilante. Back in Moscow, the new Soviet interceptor had moved from the drawing board to tarmac.
6th of March, 1964, Mikoyan Design Bureau test pilot Alexander Fedotov makes the maiden flight of the 155R1. I remember that day very well. We had a potential accident during that maiden flight. It was quite cold, about minus 12 degrees Celsius. Earlier, we'd installed sensors on the aircraft to test the flight systems in flight. We had a remote health-checking system in the sensors, and soon after takeoff, I got a warning indication that the fuel pumps weren't working. Afterwards, it appeared that an important fuel agent hadn't been added to the aircraft tanks. It was a sort of antifreeze for kerosene. As you know, kerosene contains water, and during the flight, the water froze in the pumps. Luckily, Fedotov managed to turn back to the aerodrome and land. He was very lucky to have had enough available fuel to get back. If the flight had been longer, the engines would have been shut down.
Its similarity to the Vigilante is obvious, the major difference being in the large twin vertical fins. MiG designers had less success than their American counterparts when it came to dealing with high-speed stability. This problem would plague the Russians for years to come. Back in Columbus, the Vigilante's problems were political, not aerodynamic. The Air Force had long argued that the strategic attack role was exclusively an Air Force mission. The Navy disagreed. By 1960, discourse over the Navy's role in the strategic mission had snowballed into the bitter inter-service, rivalry, and debate. The Vigilante was a casualty.
The Air Force convinced Congress that the Navy shouldn't have a strategic mission, and so we converted the airplane from a 70,000-foot Mach 2 airplane very successfully to a low-altitude, long-range reconnaissance airplane.
Enter the RA-5, R being reconnaissance. The shift from attack to reconnaissance took place just as the Vigilante was entering service with the Navy. The first Vigilantes were delivered to Naval Air Station Sanford in Florida in 1961. By January of the following year, they entered squadron service. During this period, the heated debate over whether the Navy should have a role in the nuclear deterrent cast a shadow on the Vigilante's long-awaited arrival into fleet service. Anticipating that the Air Force would get its way, the Navy recognized its potential in a very different role. The Vigilante was well suited for the role of aerial reconnaissance. Fully loaded with cameras, the recon pilot's only defense is speed. Capable of blazing beyond Mach 2, the Vigilante was clearly fast enough for the job. However, even more important than speed was the fact that it could be launched from a carrier. Unrestricted by the diplomatic and logistical problems encountered when operating from foreign airfields, the Vigilante gave naval intelligence an eye in all corners around the world.
This airplane carried fixed focal length cameras from 3 inches out to 12 inches, had an 18-inch panoramic camera that would let you stand miles offshore but still get excellent photography of areas of interest. It was also an all-weather machine because it had in that canoe underneath the airplane a side-looking radar or an image-forming radar that would go through clouds that would bring back image quality or reconnaissance quality photography. The 18-inch pan camera would give you wonderful standoff, almost the quality of today's space cameras, in that you could read a license plate in downtown, probably still classified cities, coastal cities at great distance.
In 1964, the first reconnaissance Vigilantes joined the fleet. During this period, the Cold War was again heating up, and there was no shortage of areas upon which the government wanted to keep a close eye on. When the Vigilante returned to the ship, intelligence information recorded on tape and film are rushed into a highly specialized group of rooms several floors below the flight deck. This area, known as the Integrated Operational Intelligence Center, is where all the processing and interpretation takes place. The Vigilante pilots had three basic ways of gathering intelligence. One was to fly at very high altitudes to get a picture of activity deep within enemy territory. Another way was to briefly sneak across the beach very low to obtain a detailed picture of enemy defenses several miles inland. The third was a short-range beach reconnaissance to give details of possible landing assault. All of the sensory data, whether optical or non-optical, was correlated and analyzed in conjunction with each other to provide an integrated analysis of the hostile military activity. Such intelligence is then passed on to the air wing. From this information, tactical mission planning or orders of battle can be prepared and effectively carried out. If an airstrike is called for, the attacking planes will know exactly which targets to attack and which radar signature to jam.
273 miles, approaching like that.
The information provided by the Vigilante is tactical, meaning that it gives a continuous and updated picture of the enemy during a wartime situation. Tactical recon was nothing new to the US Navy. During World War II, Navy Wildcats were fit to carry large cameras. Stationed at forward bases in the South Pacific, photo pilots flew over Japanese Hell Islands before an amphibious assault. Navy bomber pilots studied the photographs and picked their targets before setting on their way. During the Korean War, aerial reconnaissance missions were being flown off the decks of carriers. Photographic versions of the Grumman F-9F Panther brought back detailed pictures of Kim Il-sung's task forces, supply depots, anti-aircraft batteries, and troop concentrations. Later in the war, these same cameras would photograph large-scale troop buildups in the north. Troops that were discovered to be Chinese. From before the Incheon landing and through to the end of hostilities, photographic intelligence proved to be a decisive factor. The prevailing notion that the atomic bomb would deter any future conflicts had been proven false. The carrier emerged once again as the long arm of the US military, and reconnaissance planes became the eye of the fleet. Following the Korean War, US foreign policy was directed to another area of the world, the Middle East. In July of 1958, civil unrest in Lebanon threatened the already precarious political standing in the region. Also, some 2,500 Americans were living in and around the Beirut area. In preparation for an amphibious landing, photographic versions of the F-9F Cougar took over the skies of Lebanon, bringing back detailed pictures of troop buildups along the Damascus Road leading from Syria. These pictures were then used to determine exactly where the Marines should come ashore. While Navy planes were busy with tactical reconnaissance, the Air Force was keeping an eye on the US military's main area of interest, the Soviet Union. On May 1, 1960, a Lockheed U-2 took off from Pakistan on a high-altitude recon mission that would dramatically change the defense relationships between the United States and the Soviet Union. The U-2, flown alone by France's Gary Powers, never made it to Norway. On May 5th, Nikita Khrushchev announced that Powers' U-2 had been brought down 1,400 miles inside Soviet territory. Khrushchev charged America with deliberate aggression and stated that the world could be pushed to the brink of war. The ill-fated spy flight was a diplomatic disaster for the Eisenhower administration. For the State Department, It meant apologies and damage control. For the Pentagon, however, it revealed the need for a faster spy plane. When the Central Intelligence Agency was in charge of strategic reconnaissance missions, the Vigilante was being readied for the entrance into the fleet. Its prowess in the areas of speed and altitude had not gone unnoticed by the CIA. After all, the plane had been initially designed to penetrate Soviet airspace with a nuclear bomb on board. If it could penetrate Soviet airspace with a nuclear bomb, it could certainly do so with cameras. New engines specifically designed to sustain the plane at a high-altitude supersonic dash were considered by both the Navy and the CIA. However, as the CIA project was still in the planning stages, a conflict in a different part of the world was beginning to boil.
Destroyer was carrying out a mission of patrol in those waters, in international waters. When it was attacked, it replied to the attack, continued to carry out its mission today, and will do so the remainder of this week in the same waters. The President has asked the destroyer force be doubled and with an air cap, a combat air patrol be available at all times on call to it. And as I think you know, he's issued instructions that in the event of a further attack upon our vessels in international waters, we are to respond with the objective of destroying the attackers.
On August 5, 1964, the Vietnam War unofficially began. Airstrikes targeted North Vietnamese fuel deposits, suspected military installations, bridges, and roadways. However, there was one major problem. Maps of North Vietnam were notoriously inaccurate. In some instances, these maps were as much as 4 miles in error. The problem this presented to American pilots is obvious. On the ground, American troops were forced to adapt to the guerrilla tactics they faced in both jungles and towns. From the day the first American soldiers set foot in Vietnam, it was clear that fighting such an elusive enemy would prove difficult. A decade of war had left the North Vietnamese well adapted to an ambush style of warfare. Inaccurate maps aggravated the problem for American soldiers. Errors up to 4 miles created confusion about the location of crucial landmarks like hills, rivers, and villages. Precision is imperative in close air support. With absolutely no room for error, the need for accurate maps was never more clear. The Vigilante pilots entered the war in late 1964 aboard the USS Ranger. Shortly thereafter, additional Vigilante squadrons joined the combat area aboard the USS Kitty Hawk, Enterprise Forrestal, Constellation, and America. The first task of the Vigilante crews was to solve the problem of poor intelligence and inaccurate maps. In just a 2-week period, the Vigilante collected the imagery of the entire Vietnamese area, providing the US military with reliable maps for the first time. However, what the maps did not show was the complex network of trails and bridges upon which the North Vietnamese funneled supplies to the south. The Ho Chi Minh Trail frustrated the American military. Cutting off this relentless flow of supplies became a priority. However, finding it was a different story. The Ho Chi Minh Trail was not one trail, but a vast network of trails. Complicating this was the fact that most of these trails were shrouded in a thick jungle canopy. Despite this, US warplanes took aim at whatever appeared to be part of this vast supply route. As the war progressed, the Ho Chi Minh Trail would become the focus of the most concentrated bombing campaigns of the entire war. Despite the onslaught of bombs, supplies continued to pour into the south. In an attempt to reveal North Vietnamese supply routes, American planes began dumping massive amounts of what was then deemed to be non-toxic defoliant. The use of Agent Orange proved difficult and ineffective. A much cleaner way of looking within the jungle canopy was carried out by the Vigilante. The infrared sensors aboard the plane could pick up heat energy from trucks or other activity in the trail. In the first months of the war, the Vigilante had earned a reputation as an exceptional recon plane. However, it had also established a less flattering reputation. Because of its sheer size and high landing speed, the Vigilante was notoriously difficult to bring aboard a carrier.
The Vigilante community was made up of outstanding aviators, but that's because we very quickly weeded out those that had trouble at the carrier. The carrier, to this day, is the most demanding aspect of naval aviation, and that's where Vigilante pilots, the successful ones, absolutely excelled.
By the cessation of bombing in 1968, the Rolling Thunder policies had transformed many areas of North Vietnam into a decimated moonscape. But the North Vietnamese proved resilient, as rebuilding commenced immediately when the planes disappeared. Working in conjunction with American bombers became the primary role of Vigilante crews. Before an attack, Vigilante pilots would fly over a likely North Vietnamese target. After the bombing run, the Vigilante would again fly over the target to assess the damage. Because he enjoyed the element of surprise, the Vigilante pilot usually encountered little resistance before an attack. However, the post-strike flyover was a different matter.
Some of the airplanes in Vietnam were lost because their tactics were to follow up a bomb delivery mission with reconnaissance, and pretty soon the Vietnamese were smart and they knew that after they got a few bombs, they were also going to get a Vigilante.
After a massive bombing raid, North Vietnamese gunners were ready at the trigger. In the north, anti-aircraft defenses were formidable. The sound of an American plane would cause the sky to erupt into a violent hail of artillery. The policy of post-strike reconnaissance proved costly. In fact, more Vigilantes were lost over Vietnam than any other Navy plane during the war. 11 of the 18 airplanes lost were attributed to anti-aircraft artillery. Proof that when flying at low levels, even the fastest and most sophisticated airplane is vulnerable to the oldest form of anti-aircraft defense. The pieces of the airplanes seen on the boat are from a Vigilante that left the USS Kitty Hawk on its last mission. May 19, 1967. Vigilantes were flown off the decks of carriers up until the ceasefire in 1973. Designed to fly against the best Soviets had to offer, the Vigilante spent most of its career flying against a more ambiguous enemy over the skies of Southeast Asia. For American pilots, this was typical Cold War reality. During the brush fires and wars of containment that characterized the Cold War, the aircraft carrier was the strong arm of American foreign policy. For almost 20 years, the Vigilante was the eye of the fleet. And during this tenure, the Vigilante community developed a distinguished reputation.
The Vigilante community really was just that. It was a small group of about a dozen fleet squadrons, one replacement air group, which serviced both East Coast and West Coast ships out of, first of all, Sanford, Florida. Then we moved up to Albany, Georgia, and finally down in Key West, where we finally wrapped up the show. But it was a small community in that everyone knew everybody, and we had our full collection of characters. We probably had a resident village idiot or two. We had bears with sore heads, but far and away, the community was made up of very, very professional people that epitomized what in the aviation business we call crew coordination.
In 1979, the Vigilante retired from service with the Navy. Without question, it was the most effective and successful reconnaissance airplane ever to operate off the deck of a carrier. Even by standards extent, nearly 2 decades after its heyday, the Vigilante's level of performance remains extraordinary. The technological and mechanical sophistication introduced by its designers have left a distinct impression on modern aviation. One of the Vigilante's major design firsts were its horizontal ramp intakes for its engines. Such intakes are now commonplace on military planes. One look at the Navy's F-14 Tomcat reveals how much was borrowed from the sleek design of the Vigilante. The Air Force's mighty F-15 Eagle has also borrowed heavily from the four-sided Vigilante designers. But whatever became of the once feared Soviet MiG-25, the Foxbat?
About a year ago, there was a picture of a Foxbat reconnaissance version. And of course, the Foxbat looks very much like the Vigilante, and it also has the same canoe on the bottom and so forth that our RA-5C had. So I think today they are continuing to have a reconnaissance system, which we no longer have.
The MiG-25 had a fate similar to the Vigilante. When it emerged, it was deemed one of the fastest and most daunting aircrafts in the world. However, like the Vigilante, it was used most effectively when carrying cameras rather than bombs or missiles. When the Vigilante retired, with it went the Navy's ability to take an integrated picture of the battlefield. During Operation Desert Storm, it would be satellites, not airplanes, that kept an eye on the movements of Iraqi troops and Scuds. However, satellites have their drawbacks.
Desert Storm, one of the big lessons learned, quote, was tactical reconnaissance. And they still in Desert Storm had to try to get satellite data to Washington and back to Desert Storm, which was a day later instead of an hour later. Satellite has a little problem getting electronic intelligence because it only goes over once every hour and a half, We can be there continuously and know exactly where we are.
With the end of the Cold War, there are now signs that dedicated tactical reconnaissance may be re-emerging as a defense priority. In the tradition of the Vigilante, an unmanned reconnaissance system currently under development promises to give the battlefield commanders an eye in the sky.
Aviation, the art of aeronautics, began with the dreamers, inventors, and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking, dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunkworks Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth, and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortress, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. For more amazing aerial footage, and to join us in this incredible journey, check out the DroneScapes YouTube channel.
If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.